Okay, so I will start the lecture now. This is the fourth lecture on the history of the science of light. During the first two lectures, I described the discoveries which had been made from the 17th to the 19th century and which have culminated with the triumph of the wave theory of light, demonstration of interference, diffraction experiments, and also with the convergence between electricity, magnetism, and optics within the theory of Maxwell. So this was a tremendous progress. It was the first great unification in physics, and it predicted important phenomena like the existence of radio waves, of X-rays, which have been discovered a few years after Maxwell. And so a lot of very important development, not only in basic science, but also for applications. In spite of all these successes, there remained some puzzling questions which classical physics could not resolve. I mentioned to you the famous lecture of Lord Kelvin, who said that there were two clouds which were obscuring the sky of physics at the very end of the 19th century. The first cloud had to do with the velocity of light, the fact that it seemed impossible to measure when an observer was moving with respect to a light source, to combine the velocity of light with the velocity of the source. The velocity of light seemed to be a constant for all observers. And this led, of course, to Einstein, to the theory of relativity, first special relativity and then general relativity. And this was the topic of last week's lecture. Now, I would like today to come to the second cloud of Lord Kelvin. He mentioned the fact that it was impossible within classical physics to understand the properties of heated radiation, light, electromagnetic waves radiated by heated bodies. This was called the ultraviolet catastrophe because it led to a divergence of the electromagnetic energy at high frequencies. And here again, something new had to be done, some classical physics has to be abandoned for new principles. And this was, of course, the emergence of quantum physics at the beginning of the 20th century. Quantum physics, which had even more consequences, was I think, even more important than relativity to completely change our vision of the world. And there are two characters, two scientists who played a very important role at the beginning of this story, Max Planck and Albert Einstein. And again, Einstein played a very important role, also very different from the one he played in relativity theory. So in this lecture, I will start to tell you about this story. I will try to describe how interrogations about light phenomena, which could not be explained by the principle of classical physics, when you try to combine Maxwell equation with the principle of thermodynamics, have led to the emergence of the quantum concepts. And I would like to follow the evolution of the ideas between 1900 and 1925. 1900 is the year where Planck started this revolution, and 1925 is the year when the modern theory of quanta, the mathematical framework of the quantum theory, was invented. In between, a lot of things happened that I would like to describe in today's lecture. And I will remind you the central role played by Einstein again in this story. So I will talk about the black body radiation puzzle, the introduction of the photon in physics, the photoelectric effect, the wave-particle duality, the heat capacity of solids, and the first atomic theories, Bohr-Sommerfeld theory of the atom, the discovery of stimulated emission by Einstein, and I will end up by the discovery of new statistics for atoms, Bose statistics and the prediction of the Bose-Einstein condensation, and the Pauli exclusion principle, and the introduction of the Fermi-Dirac statistics. And what is remarkable is that all this happened before the quantum theory was firmly established. It happened during the year of what is now called the old theory of quanta, but I think it's a very interesting history, which plays of course, a very important role in the history of science at large. So the whole thing has started with, I may say, with two papers, and I show you here two papers published in German. The first one is a paper by Max Planck, which was published in December 1900. It's very symbolical because this was the last days of the 19th century. And Planck published a paper called, translated in English, on the theory of the energy distribution law of the normal spectrum. So he solved the puzzle, the fact that nobody before had been able to describe mathematically the shape of the thermal radiation, the spectrum of the thermal radiation, and he started this revolution. And of course, the second paper is a paper published by Einstein in 1905, in March 1905, called On a Heuristic Viewpoint Concerning the Production and Transformation of Light. So it's a rather philosophical title. What is remarkable is that this is one of the four papers published by Einstein in the year 1905. This is the first one. The next one was a paper on special relativity, and there was a paper on Brownian motion, and another paper on relativity, all published during this miraculous 1905 year. So what was the problem? What is this ultraviolet catastrophe about? At the end of the 19th century, it became important to try to measure the temperature of furnaces, of ovens. It was an industrial revolution. There were ovens which were melting metals at very high temperature. And of course, it was impossible to put a thermometer in the oven. And people realized that by looking at the light, which was radiated by heated bodies, it was possible to infer the temperature because there was an universal law. The radiation coming from heated bodies was independent of the body, which was heated, dependent only on temperature. And it was called the black body radiation because if you consider an oven, the inside of the oven has walls which are black, which absorb all the radiation which falls on them. But if you heat them, they will emit radiation. And this radiation will get in equilibrium with the walls. And if you make a small hole in the oven, through this hole, radiation will escape. And people started to study the spectral distribution of this radiation. And they found many very basic phenomena. One of them is that the spectrum of the light which is escaping depends only on the absolute temperature. And the intensity versus frequency has a bell-shaped curve. That is, at very low frequency, at very long wavelengths, the radiation is very weak. It increases, it passes through a maximum, and then in the short wavelengths, it decreases again. There is a maximum, and this maximum depends on temperature. And there is a very simple law saying that the product of the wavelengths by the temperature is a constant. That is, the higher the temperature, the shorter the wavelengths. And the constant is called Wind's constant, and it was known at the time of Planck. The maximum shifts towards short wavelengths as temperature rises. At room temperature, in this room, all the bodies radiate, but they radiate in the infrared. You don't see it. And you would have to heat them to a very high temperature for this radiation to come into the visible part of the spectrum. So what was the problem? The problem was that if you applied classical theory, what you found is the curve that I showed on this figure, the fact that classical theory predicts that the radiation should increase continuously as you shorten the wavelengths, and you have a divergence at short wavelengths. And this was called the ultraviolet catastrophe. And of course, this result was absurd. Where does it come from? I tried to explain this on this slide. In fact, the calculation was made by two English physicists, Rayleigh and Jeans, at the end of the 19th century. And the assumption was, and as all the other scientists at that time, was that the field, the electromagnetic field, is made of modes. Of course, waves and electromagnetic waves are a superposition radiation at different wavelengths, and each mode of radiation behaves as a small harmonic oscillator. And you have just, if you want to know how many oscillators you have to count the number of oscillators in a given volume. And to do that, it's useful to define what is called the wave vector of radiation. Wave vector is a vector which is along the propagation of the wave, and its amplitude is inversely proportional to the wavelength. In other words, the K vector is just the frequency, the spatial frequency of the radiation. And the first thing you have to do if you want to know how much energy you have is to count how many radiators you have in a given window of frequency. And this is a very classical calculation in electromagnetism. And I try to explain it on this transparency. In fact, the wave vector has three components, kx, ky, and kz. And each of these components evolves by steps of 2 pi over L, where L is the dimension of the box. To simplify, I assume that the box is a cube of side L. And you see that you have a discretization of the wave vectors given by this formula. So to try to explain, this is very straightforward, but to try to explain it, I have added a slide here, which you don't have in your notes. This slide says that if you want to count the modes, what you have to count is how many wavelengths you can accommodate between the walls of the box. It's a little bit like if you have to count the different modes that the string can oscillate on. The string, which is fixed at two ends, can accommodate vibrations which has an integral number of wavelengths or half wavelengths between the endpoints. Here it's the same. You have to count the number of wavelengths you can put between the mirrors. If you put only one wavelength, as I have shown here, K, which is 2 pi over L, is just, you see that if lambda is equal to L, then K is equal to, which is equal to 2 pi over L, is just 1 time 2 pi over L. Now, if you have two wavelengths between the mirrors, then lambda is L over 2, and K is 2 times 2 pi over L. So you see that you have this periodicity, 2 pi over L for K, and all the integral N are possible. Now, what you have to count is how many modes you have which have their K vector bit comprised between K and K plus dk, because this will tell you how many modes you have in a given energy interval, because dk is proportional to d nu in a frequency interval. So you have to, it is very simple. What you do is you compute the volume between a sphere of radius k and a sphere of radius k plus dk. So it's 4 pi k squared times dk. And how many modes you have here is how many boxes of size 2 pi over L cube you can put in this volume. And so this is a formula which I show you now. You see that the number of modes is just k pi k squared dk divided by 2 pi over L cube. 1 over L cube is just comes here. So L cube is just the volume of the box. And you find that this number in the interval dk is given by this formula. It's proportional to V and to k squared dk. Now you have a simple formula like that. You have also to multiply by 2, because for each k vector, you have two polarization, two transverse polarization, which are two independent modes. And you get this formula, which was the formula used by Rayleigh and Jeans. This is the number of oscillators in an interval of wavelength of wave vectors dk. So now I come back to this slide. This is the formula written here. And if you replace k by 2 pi over nu, by 2 pi nu over c, you, instead of k squared dk, you get nu squared d nu, and you have this formula. So the number of modes increases as nu squared. And this is quite clear. If you have a big box, you will put a lot of modes, so it's proportional to V. And in a given V, the bigger is lambda, the more mode you can put, because you can have much more oscillation between the two mirrors. So this formula is quite simple, but then Rayleigh engines used thermodynamics, and they said, they invoked the equipartition of energy. They said all these modes should share the thermal energy, and each mode, it's kind of democratic principle of thermodynamics, each mode should have the same energy as any other, and each mode should have an energy K Boltzmann T, where K Boltzmann is the energy per degree that Boltzmann had introduced in the theory of thermodynamics. So if you do that, you find that the intensity, the spectral density, you divide by V. In fact, what they compute is the energy per unit volume, and in a given frequency interval, I nu is a spectral density once you have divided by the volume and the frequency, and they found this formula, which is quite simple, but which leads to this absurd result. The intensity diverges when nu increases. So first of all, you don't have a maximum. It's just keeping increasing. And second, if you integrate over nu, you get infinity, which is completely meaningless, physically meaningless. You cannot say that you have an infinite amount of energy, whatever the temperature is in the box. So this was a contradiction at the same level as the one I discussed last week. Last week, I told you that Maxwell's equations were contradicting Galileo's principle of classical relativity of motion according to Galileo. So something had to give up, and in fact, the Galilean transformation gave up for Lorentz transformation. Here again, you have something which is wrong. You cannot have at the same time Maxwell's equation, assuming that everything is continuous, and equipartition of energy. So something had to give up, and this is what was understood, not clearly understood, but at least hinted at by Planck. But before that, I would like to recall you, we have to make a digression in simple thermodynamics to understand what's going on and where does the equipartition of energy come from. In fact, the first principle of thermodynamics is the conservation of energy, which is quite simple. Everybody knows about it, which had to be modified in relativity by assuming that energy and mass are the same concept. Now, the second principle of thermodynamics tells you how the system evolves in time toward which equilibrium they go under different conditions. And one very important problem is what happens in a system which is in thermal equilibrium with a reservoir, which is kept at a constant temperature because it can exchange energy with a reservoir with boundaries around it. And what the second principle tells us is that under this condition, the system tends to increase its what is called its free energy and to get the maximum possible value for its free energy. And what is the free energy? The free energy, F, is the energy minus T times S. T is the temperature, and S is the entropy, which measures the disorder in the system. And so you see that what the second principle tells us is that nature is at the same time lazy, and messy. It's a very simple way to remember. What is laziness means? It means that the system wants to get as small an energy as possible to decrease the free energy. The principle is a minimum. So it tends to get to the smallest possible energy. And what messiness means, it means that if you want to minimize E minus TS, you have interest to maximize S because there is a minus sign. So maximizing S is maximizing the disorder. So the system wants at the same time to have the minimum energy and the maximum disorder. And of course, it has to compromise between these two things. And I have tried to show you an example here. What happens, assume that you have a box, and inside the box you have a gas of atoms or molecules. And the energy is measured, the gravitational energy, mgh. The temperature is fixed. It's a kind of isothermic atmosphere. Assume that the atmosphere above us is a column of gas at the same temperature. What will happen? if the temperature is very low, Ts does not count. What counts here is E. So the system will try to get all the molecules will go at the bottom. In fact, you know that what will happen in the end, because the molecules are in fact also interacting with each other, that they will freeze and they will become a liquid and then a solid. But I don't want to enter into that. I assume there are no interaction. Then the molecules will try to go down and to be as low as possible. What happens in the opposite case? In the opposite case, if T is large, in E minus Ts, what will count is minus Ts. And then the disorder will be maximum, which means that the molecules will be everywhere. And in the middle, what will happen in the middle, if the temperature is intermediate, then of course what you will have is a situation where there will be more molecules at the bottom and less molecules, and it will be an exponential law, and this is a Boltzmann distribution. So this is a Boltzmann distribution is a compromise between minimum energy and maximum disorder. And when you do the calculation, what you find is that the distribution of molecules obey to the Boltzmann distribution. It's exponential of minus E over K Boltzmann T. And K Boltzmann is a parameter which is important here. K Boltzmann T is what you have to compare to MGH. If MGH is large compared to K Boltzmann T, low temperature, the molecules will go down. If MGH is small compared to K Boltzmann T, the molecule will be everywhere. And the exponential law describes all this in a quantitative way. So this is what we knew from, people knew from thermodynamics at the end of the 19th century from the work of Boltzmann, Gibbs, and others. So what Rayleigh and Jeans did was to assume that each oscillator could take any energy, E, varying from 0 to infinity, with this Boltzmann law that you see here. And of course, you have to put a 1 over Z factor because you have to normalize the probability. The sum of probabilities have to be equal to 1, of course. So, because this is a probability, what I'm computing here is a probability that an oscillator has a given energy. So the fact that the sum of the probabilities, the integral of the probability is equal to 1, allows you to compute Z. It's a very simple calculation. You find KBT. So Z, 1 over Z is just 1 over K Boltzmann T. And then if you want to compute the average energy of this oscillator, what you do is that you compute sum of E, PD, dE. So the energy is E with probability P of E. So you have to integrate this. This is a very simple integral, and you find KBT. This is the occultation of energy. So this is the result, which leads to the UV catastrophe. So something is wrong. What is wrong? And of course, it has been discovered not immediately by Planck, but he hinted to that. What is wrong is to assume that the energy of an oscillator can vary continuously. And what was introduced by Planck is the fact that the energy varies in steps, delta E nu, the steps being proportional to nu. And the proportionality constant, H, is Planck's constant, which was introduced in physics in 1900. And you see that H has a dimension of an energy divided by a frequency, which is equivalent to energy multiplied by time. And this reminds us something about last week's lecture. An energy multiplied by time is an action. So H is a quantum of action. It's fundamentally, an action is measured in joule time seconds. And so if you assume that, what you see, it seems innocuous. It's okay, instead of a continuous integral, I will sum discrete quantities, but see what happens. Now, this integral over energy becomes a sum over n, n being the number of steps that you do in the energy scale. You have either 0 or 1 or 2 or 3 times h nu. So you have to sum this. And if I introduce the dimensionless factor h nu over kt, I can get x out, and I get kt over z, x time this sum over n of n minus e n x. I remind in the notes, there is this print, you should have an n here, which is missing in the lecture notes. So in fact, what you have to compute is, again, Z and this sum here. And these are very simple things to compute. It's a sum of exponentials. So I show you the calculation here. First of all, the normalization constant Z is just a sum over n of e minus nx. So it's an exponential series, and it's 1 plus e minus x plus e minus 2x plus so on. And this is just 1 over 1 minus e minus x. It's a very simple result. And you immediately realize also that the other sum that you have to do, this one, is just minus dz over dx. You just derivate this and you find e minus x over 1 minus e minus x squared. And then you have to combine these two results, which is done on the last line here. And you find that E is equal to kt times x over e power x minus 1. So you see that there is a correction to the equipartition of energy. It's not kVt, it's kVt times this. Now, if x is very small, what does it mean, x small? It means that the temperature is large, or the frequency nu is small. You see that now e to the x power minus 1 is equivalent to x, because e to the x is 1 plus x. So you find that this factor goes to 1, and you recover the equipartition of energy with K Boltzmann T. But if x is large, that is, if the temperature becomes small, then this factor completely goes to 0, and the energy, average energy in the oscillator decreases. So in fact, the excited states of the oscillator are frozen. The system remains in the ground state because of this fraction here. So what does it mean? I try to summarize this. Now what we have for the energy of each oscillator is a ladder of equidistant states. And the important parameter is K Boltzmann T. You see that if K Boltzmann T is large compared to the steps, here it's 3 times the step or 5 or 6 times the step, then the system can, to increase the entropy, the system can populate excited states. So to some extent, it will populate excited states, and there will be the exponential Boltzmann law, and the equipartition of energy will be a good approximation. But what happens if you increase the frequency, or equivalently, if you decrease the temperature, then you see that it will cost too much energy for the system to be disordered. It will prefer to stay in the ground state than to populate excited state, because if it does it, the entropy will, of course, increase, but the energy, it will be at the cost of a too much increase of the energy. And the compromise is, of course, an exponential law. But then you see that the UV catastrophe is avoided because the excited state of high frequency oscillators are frozen. So you have to understand there is something which is important here. What is quantized here is not the frequency. The spectrum is continuous. You have all the frequencies in the spectrum. What is quantized is the distribution of energy in each of the oscillators by step of each. And of course, if you now use this result, you get Planck's law. You have here the average energy per oscillator. At low frequencies, you recover the Rayleigh-Jeans approximation, and at high frequencies, the modes of high frequencies of short wavelengths are frozen. They're not excited. What you have to do now is multiply this by the number of oscillators in a given frequency range, then the calculation of Rayleigh-Jeans remains correct. But now you see that instead of having kt here, you have this function, 1 over 8 e to the h nu over kt minus 1. You can also express this in terms of wavelengths. You remember that lambda is equal to c over nu. So instead of computing I of nu, you change a variable and you compute I of lambda. You get this expression for I of lambda, and you get these curves here, which are given by Planck's law. And in fact, these curves describe very, very accurately the radiation of the black body. In fact, it's an accuracy absolutely fantastic. Now, 100 years later, we receive the radiation from the universe, which is called the black body radiation background of the universe, and it plots this Planck's formula with fantastic precision. It is one of the reasons why the satellite, which is recording this black body radiation of the universe, was called the Planck satellite, 100 years after Planck's discovery. So, and of course, there was only one free parameter here. The free parameter is h. What do you have to take for the step? And what Planck did is just to fit this curve to the experiment. And he found the value of h, which is the only one which gives a good fit. And this value is shown here. It's 6.626 10⁻34 joule second. And this is Planck's constant, which will play, of course, an essential role in all of quantum physics later on. So Einstein came something like 5 years later. Planck had some resistance to say that the field was quantized. He tried to say that, in fact, it was not the field which was quantized, but that for some reason, the exchange of energy between fields and matter were quantized. So he was reluctant to abandon the idea that the field itself was just a wave. But Einstein, excuse me, in 1905, in the paper I showed you before, said he did a very clean thermodynamical calculation and said all this tends to prove that light is made, in each mode of the light, you have real quanta of energy, which were later called photons. And he said that the photons propagate at the velocity of light. Each photon carries an energy h nu. So it has to carry a momentum in a plane wave h nu over c, which is h over lambda, and this will play an important role later. This is a correspondence between energy and momentum that he got from relativity, but it's valid here. What we will see also is that if the light is polarized circularly, each photon carries 1 unit of angular momentum equal to plus or minus h over 2 pi, and this h over 2 pi is called h bar. So it's a Planck constant divided by 2 pi, and h bar is a parameter which will intervene in many formulas. Just to give you an idea, if you compute the energy of a red photon, compute h nu for a red photon, you find something of the order of 2.6 10⁻19 joule. And of course, it's so small units that you prefer to count in atomic units, which are more, which have an order of magnitude more convenient. And the unity of energy at this scale, at the atomic scale, is called the electron volt. It is the potential, the energy which is released by an electron which falls by 1 volt in an electric field. And 1 electron volt is 1.6 10⁻19 joule. So in electron volts, you find that this photon has an energy of 1.65 eV. Now, if you do a calculation, try to compare with what we have in our everyday life, a lamp which has a light power of 100 watt emits 3.8 10 to the 20 photons per second. So the number of photons is so huge that this granularity, this discreteness is completely invisible. But in spite of that, in spite of the very small value of the energy for a single photon, it has a very deep consequences. We understood that, first of all, that it explained the property of the black body radiation, which is not explained if you assume that h is equal to 0. And it explains also other phenomena, among which another very important phenomenon, which was also discussed by Einstein in the 1905 paper, which is the photoelectric effect. And Einstein said, if we assume that the light is made of grains of energy, of quanta, then we understand a very puzzling phenomenon about the photoelectric effect. What people had, the photoelectric effect was discovered by Hertz at the end of the 19th century, when if you send light on a piece of metal, electrons will be extracted that you could collect by making a difference of potential. So you can accelerate the electrons which are emitted by the metal. But the very strange feature is that the amount of electrons that you extract is not proportional to the energy. If you have a very intense light, but which has a long wavelength, for example, if you put a lot of red light, no electrons will come out. But if you have just a faint light blue, then the electrons will go out. So what Einstein understood is that the process of photoelectric effect, this process is a process in which one photon kicks out one electron from the metal. And for that to happen, h nu has to be larger than the extraction energy. The electrons are kept into the metal, they are attracted to the metal, and each electron needs an energy W to get out. Even if you have a lot of photons, but each photon not having the energy h nu, nothing will happen. On the other hand, if you have the right energy, if h nu is larger than W, the difference will be the kinetic energy of the electron going out. The energy is conserved, so one part of h nu is used to extract, and the rest is used to give the electron its velocity and its kinetic energy. And so Einstein said the kinetic energy of the electron will vary linearly with the excess of, with h nu minus h nu 0. And if you measure the slope of this variation, you will find Planck's constant again. And Millikan, an American physicist, made the experiment a few years later. He confirmed that the slope was indeed h, and this is the reason why Einstein got a Nobel Prize in 1921. It was not about relativity, not about special relativity, not about general relativity. It was not even about quanta photons. It was just because he had understood the photoelectric effect. And at that time, even in 1921, some people did not believe in the quantization of the field, even Planck. In fact, Planck was very reluctant to accept that for reasons that I will try to discuss now. If you think about it, the photon introduced something revolutionary in physics. He says that light can be at the same time a wave, because of course you have the interference effects have not disappeared, Maxwell's equations are still valid. So light is a wave, but at the same time it carries discrete units, which are photons. And so this introduced in physics what is called the wave-particle dualism, the wave-particle duality, which is something very strange for a classical mind. For instance, how can you reconcile that with the superposition principle? Waves can superpose, interfere with each other, but can particles interfere with one another? What does it mean? And this, in order to understand that, we need a lot of reflection, a lot of going back and forth between theorists, and I will discuss that mostly in next lecture. But there is a very puzzling fact here. And this I have tried to illustrate with this. It's called an ambigram. It's something that you can read in different ways depending upon your psychological mind, the state of mind. Here you can read light is a wave or light is a particle. This is called an ambigram. It's kind of game with letters, which has been drawn by Douglas Hofstadter, which is an American scientist. So as we will see in quantum physics, depending upon the kind of experiments that you do, you will read it either as a wave or as a particle. And this is a principle of dualism between the wave and the particle aspect. It has been introduced about photons, but we will see that it extends to matter also. Another point here, you remember that the first centuries of the history of light were dominated by the dispute between Huygens and Newton. And so apparently, Einstein has reconciled it. He has said, yes, light is a wave. Absolutely, Maxwell's equations are valid. And in fact, all relativity is based on Maxwell's equation. So Einstein did not give up Maxwell's equation. But light is also made of particles, which was Newton's point of view. But I am sure that this kind of reconciliation would have surprised very much Huygens and Newton as well. So we'll have to talk about that in many more details. So let's go on. This was 1905. Then many years passed, and Einstein understood that, in fact, this idea of quanta was much more general than Planck's law. And he understood that he could explain with this theory of freezing of quanta of high energy, it could explain the anomalous properties of the heat capacities of solid. So what is that? If you heat a body, you have to provide energy, and the energy you have to provide per degree is called the heat capacity. And what had been shown in the 19th century is that for a lot of solids, in particular for a lot of metals, the heat capacity per atom, that is the energy that you have to provide to per atom to the sample, is 3 kBt. And this was understood by Boltzmann, who said in a solid, the atoms are vibrating around their equilibrium position, and each atom is a 3D harmonic oscillator because it can vibrate around X, Y, and Z. So you have kBt per oscillator, that makes 3 kBt, and that explains the properties of a lot of solids. But now you have some solids like diamond, which is a form of carbon, for which the heat capacity was much smaller than 3 kB. In fact, for carbon, it's less than 1 kB. And so Einstein said, okay, but maybe it's the same thing at the Planck's law. It turns out that in carbon, because carbon is very rigid, the frequencies of oscillation are very high. They are much higher at room temperatures than kBt, so the degrees of freedom must be frozen. And if they are frozen, you will fall below 3 kBt. So he made the calculation, just use Planck's law. But instead of saying that the oscillators were modes of the field, he said the oscillators are just mechanical oscillators of atoms in matter. And he found the heat capacity is obtained by derivating the energy with respect to temperature. So this is a very simple operation that you can make. He found the result, which I show here. And this result, if X is small, you find 3 kB, but if X becomes large, you fall below 3 kB. So again, the same story as before. And this explains that the heat capacity of carbon is smaller. If you want to retrieve the 3 kB, you have to heat the carbon very high. On the other hand, most metals which give 3 kB at room temperature see their heat capacity going down at low temperatures. At very low temperatures, the heat capacities of metals is going to 0, which is again a consequence of this formula. So this was in 1911. Einstein went to the first big gathering of physicists of the modern era, which was a Solvay conference in Brussels. It was a very rich Belgian industrialist, Solvay, who gathered all the great physicists of the time to discuss these new quantum ideas. And I just will make a little diversion here to show you this picture, which is a very famous picture, which shows this 1911 Solvay conference, in which you can recognize a lot of characters that we're talking about. You see here Einstein, which was rather young. He was 31 or 32 years old. He was still standing. The important people were sitting, where Einstein was still young and considered as a junior scientist. So he was standing. Near Einstein, you see Paul Langevin, who is the guy, a friend of Einstein, the guy who invented, who describes the twin paradox, and we talk about Langevin again in the following. On the other side of Einstein, you have Kamerlingh Onnes, who is a Dutch physicist, who on that year discovered superconductivity, which is another quantum effect. So you see, and standing near Kamerlingh Onnes, you have Rutherford, and I will be talking about him in a moment. And behind Rutherford, you see Jeans, who is a guy of the Rayleigh Jeans formula. And sitting at the table, you have Poincaré, who discovered the Lorentz transformation. At the other end of the table, you have Lorentz sitting. And here you have Jean Perrin, we're talking about him, Marie Curie. And on the other side, you have Planck, who is standing here. And who else? Also, I want to show you, this is Marcel Brouilloin. Marcel Brouilloin was a professor at Collège de France, like Langevin, and he was a secretary of this Congress. And he took all the notes, and in the library of the Collège de France, we see there is the proceedings of the 1911 conference, with in particular the paper by Einstein about the heat capacity of solids. So what Einstein discovered is that H is a universal constant. It intervenes not only in the Planck's radiation law, but it intervenes also in the heat capacity of solid and in many other aspects of physics, as we will see in a moment. In fact, at that time, one started to understand the quantum nature of atoms. And for that, I have to remind you that in 1897, J.J. Thomson, an English physicist, had discovered the electron in cathode rays. And of course, if you have electrons in matter, which are negatively charged, you need to have positive charges to get neutrality. And so the model of Thomson was called the plum-pudding model. He assumes that electrons were embedded in a jelly of positive charges. So it was the first naive model for the atom. Until 1911, at the time of the Solvay meeting, when Rutherford made a very dramatic experiment. He took a very thin gold foil and bombarded it with alpha particles, which are produced by radioactive phenomena, which were discovered by Curie. And these alpha particles bombarding the gold metal were going through the metal, except in very rare instances where they were coming back. So it was absolutely fantastic. You had a very thin foil. You were shooting energetic particles and they were bouncing back at you. So immediately people understood that most of the matter was concentrated in very small volumes. And so the electrons were around. And this was, of course, the idea that atoms were made of a very small, very heavy and small nucleus around which electrons were gravitating. And this is a model that Rutherford and Jean Perrin in France developed. It was a planetary model of the atom. But at that time, it was a kind of classical model. It was a kind of solar system in miniature, a very small solar system in which electrons were going around the nuclei. Then 2 years later, in 1913, a postdoc of Rutherford, the young Niels Bohr, built the first quantum model for the atom. He said, okay, we have to understand the fact that the electron is going around like the Earth around the sun, but we have to understand something, the fact that the spectra that the atom emits, and this was known since the 19th century, the spectrum is discrete. And for that, you have to admit that the energy levels of the atom are also discrete, are quantized. And so as the harmonic oscillator are made of discrete levels, the energies in the atom are also made of discrete steps. And he describes what is called now the Bohr atom. So you have an electron going around on a circle, either on the first orbit, the second orbit, or the third orbit. And the energies are given by discrete steps of the ladder. The difference with the harmonic oscillator is that the levels are no longer equidistant. The third level is much closer to the second to the first. And he computed, and I will tell you in a moment how he did it. And he found that the radius, the Bohr radius, is proportional to, there is a principal quantum number, a number n, which takes the value 1, 2, 3, and so on. And the radii which are allowed for the electron are A0 n square, where A0 is the Bohr radius. So the radii increase as a square of the principal quantum number. The energy, which is inversely proportional to the radius, it's a Coulomb's law. So the energy is 1 over r, so it's 1 over n squared. And the spectrum that you can see correspond to the energy difference between two levels. When the atom goes from one, when the electron jumps from one level to another one, it emits or absorbs a photon with h nu equal to the difference of energy. So there is conservation of energy, but of energy which take discrete steps. And this explains the spectrum of the hydrogen atom, which was not understood before. The spectra had been observed since the 19th century, but their nature remained mysterious. How did Bohr do that? What Bohr did is to quantize the angular momentum of the electron on a circular orbit. You know, what is an angular momentum? It's a momentum mv times r, mvr. And if you look at the dimension, mvr is again an action. It's like px in the et minus px term. So you have an action here. And so the reflex at that time was intuition. If you have an action, the action should be quantized in unit of h. In fact, h bar, h over 2 pi. And so he assumed that on circular orbit, you have m omega r square, which is the angular momentum of the circular orbit, is equal to n h bar, multiple of the quantum of action divided by 2 pi. So you have one equation. Now you have another equation, which is the equation of Newton equation, m omega square r, which is mv square over r, which is the centrifugal energy, has to be equal to E over R. This is equilibrium on the orbit. The attraction to the nucleus has to be balanced by the centrifugal energy. So you get another connection between omega and R. You replace Q square over cat pi epsilon naught by E square to simplify notation. And what you get now, when you have these two equations, you solve for omega and for R, and you find the result that I showed on the previous slide. I let you do the calculation. It's very simple. So it's a very simple calculation, like a high school kind of calculation on a circular orbit. What also is interesting is the last lines of this equation. It's instructive to express everything in terms of the quantity alpha, which is E square over h bar c. If you look at the units, this quantity is dimensionless. E square of hc is equal to 1 over 137. This quantity is the same whatever the units you take to describe, and this is an absolute number which tells you something about the intensity of electromagnetic forces. This is a constant of electromagnetism, which tells you that electromagnetic forces are rather weak forces because this factor is small compared to 1. In fact, what does it mean? It means that if you compute, if you use alpha and replace in all these formulas, you find that the energy of the electron on the nth orbit is alpha squared mc squared, which is just a relativistic energy containing the electron, divided by n squared. Alpha squared is about 1 part in 10 to the 4. So you see that the binding energy of the electron in hydrogen is 10 minus 4 to 10 minus 5 times the relativistic energy. So it's a small relativistic correction. You also see, if you look at the velocity of the electron on the nth orbit is c over n multiplied by alpha. So even for n equal 1, even for the ground state, the velocity is 1/100th of the velocity of light. So there are very small relativistic correction. It explains why you can understand very well hydrogen in non-relativistic terms. So this was Bohr's contribution. And about 2 or 5 years later, or 3 years later, Sommerfeld in Germany extended Bohr's idea. He said, why does Bohr consider only circular orbits? In this problem of a particle going around a central force, you have elliptical orbits too. And what elliptical orbits are, these are orbits which have smaller angular momentum. The circular orbit has the largest angular momentum. And if you take elliptical orbits, they have smaller angular momentum, but the angular momentum is also quantized. And what happens is that all these orbits have the same energy. So you see that, in fact, the nth orbit is degenerate because states with different energy with different angular momenta have the same energy. And Sommerfeld understood that. In fact, this is very strongly related to Kepler's problem of planets around the sun. In the notes, I made a mistake. You have to put K, which is the angular momentum in Sommerfeld theory, takes the value 1, 2, 3, 4, and the maximum angular momentum is for a circular orbit. I don't know why in the notes you have m equal plus or minus 1, which is meaningless. also want to say that Sommerfeld understood that it was an approximation because it's a classical calculation. So what happens when the electron gets close to, on a non-circular orbit, when the electron gets close to the nucleus, it goes faster. If it goes faster, it becomes heavier because of relativity. And so you have a relativistic correction, which will break the symmetry of the classical problem. In fact, what we found when you do that is that the orbit, instead of being closed, start to be open, exactly like Mercury in the astronomical problem. And so you have a correction to the energy due to relativistic effects. Different angular momentum states have different energies. There is another reason for that also, is that because of the spin of the electron, the magnetic moment, which was not known at that time. So what is called the fine structure, the fact that you have departure from the degeneracy of the nth level, was not well understood, but Sommerfeld was the first one who had a hint, started to understand this. So we are in 1916, and I want to finish before the break, by another great discovery of Einstein made in 1916. I remind you that last week we saw that Einstein was very busy with the general theory of relativity between 1907 and 1915, the end of 1915. He presented the theory of general relativity at the Prussian Academy of Sciences in December 1915. So during that time, he left the quanta on the side because he was too much excited by relativity. And then when he solved the relativity problem, he came back to the quanta, and he found out that a lot of things had been understood about the quantization of the atomic levels. So not only radiation was quantized, but the atoms were quantized too. And so Einstein said, okay, maybe now I can come back, revisit Planck's law, and try to understand Planck's law by looking at how, really microscopically, how the photons interact with matter. Matter is made of discrete energy levels. When a photon is absorbed, the atom is jumping from lower level to the upper level. When a photon is emitted, the atom is jumping from up to down. What Bohr had said is that the process of emission is a random process. You cannot know when an excited atom will spontaneously emit a photon. You can only predict the probability of emission, but not the exact time. So this was called spontaneous emission. And you had absorption. So Einstein said, okay, I will look at the balance between the effect of absorption and spontaneous emission and see whether I find Planck's law or not. And I show you on the next transparency, the next slide, what Einstein did. So he assumed that the walls of the oven, the walls which were containing the thermal radiation, were made of atoms with all possible couple of energy states, so that the atoms could interact with the whole spectrum of radiation. And he looked at the subset of atoms which have a transition at the frequency nu. And he said, can I understand the equilibrium of the light at frequency nu with this class of atoms which can emit or absorb light at frequency nu? So what is the process of absorption? Absorption brings the atom from the state 0 to the state 1. And the ratio between the population of 0 and 1 is just Boltzmann factor. You have more atom in zeros than in 1 in the ratio E minus h nu over kT, because the atoms are in thermal equilibrium in the walls. So what happens to, how does N naught change with time? dN0 over dt is, of course, decreasing because of absorption. And the decrease, the rate is proportional to the intensity of the light, proportional to the number of atoms in the state N0. And there is a constant in front, which is called the A coefficient, the A Einstein coefficient, which depends on frequency. And of course, if the rate at which N naught decrease is given by that, N1 increased by the same amount, because the sum of the population of N naught and N1 remains constant. What leaves N naught goes to N1 and reciprocally. So this is the absorption process. Then he looked at the other process, which is spontaneous emission, which was a process discussed by Bohr. And in spontaneous emission, what happens is that the atoms which are in state 1 go back to state 0. So dn0 over dt is positive, proportional to n1, and dn1 over dt is negative, proportional to n naught. And again, the sum of the two is 0 because what goes from one level leaves the other. So he had these two processes, and then he wrote the equilibrium between the two. So you assume the balance. So you see that you must have the equation that I show you here. dn naught is equal to minus dn1. And so you have these two terms. This term is the absorption. This term is the emission. It has to be equal to 0. So you get I nu equal to this. And you see that I nu is given by a Boltzmann distribution. So this is not Planck's law. The temperature dependence of I nu is not the one of Planck's law. So there is something wrong. Something is missing. And Einstein was puzzled by that. And then he said, okay, now let's assume that I have a third process, which he calls stimulated emission, which is symmetrical from absorption. That is, if the atom is excited, it will go down in the ground state by emitting a photon. And the process is exactly symmetrical from the absorption. In absorption, the atom goes from down to up by absorbing a photon. Here he's going from up to down by emitting a photon. And he does it at a rate which is proportional to the number of photons already existing. So it's an emission which is stimulated by the photons which fall on the atom. So if you admit this equation here, so you see that now, this is that n naught increases proportionally to n1, but also proportionally to the intensity of radiation at this frequency, with a coefficient which is the same as the one you had for absorption. And you have this equation, and now the detailed balance, which gives you the equilibrium, has three terms. The red term, which is the absorption, the blue term, which is spontaneous emission, and the third term, which is stimulated emission. And from that, you can extract I nu. And when you extract I nu, you find that I nu is equal, there is a constant here, but it is equal to n1 over n naught minus n1. And this is exactly the Planck's function. So he recovered Planck's law by adding a process which is stimulated emission. And I talked to you about that, but stimulated emission is very important. It is the phenomenon which is at the basis of the laser. And this was in 1916. It was 45 years before the first laser was invented. So on the next slide, I summarize this. What Einstein said is that there are three processes by which a two-level atom interacts with photons. The first process is just absorption. The atom in the ground state absorbs a photon and gets in the excited state. The second process is spontaneous emission. An excited atom goes back to the ground state and emits randomly a photon in any direction. And the third process is stimulated emission. You have an impinging field on an excited atom. The atoms fall down and add a photon to the existing field. So it's an amplifying process. It's a process by which radiation is amplified by atoms. And this amplification process, as I told you, is at the basis of the laser. The first laser was invented in 1960. So the principle is the following. What you need to do for a laser to work is to have more atoms in the excited state than in the lower state, because you want stimulated emission to overcome absorption. So you cannot be in thermal equilibrium. You must be in an inverted situation where you have more atoms excited than the ground state, which is what you could call a negative temperature, because the Boltzmann law with a negative T would give you that. And in fact, the big problem to build a laser was to find an efficient mechanism to bring atoms in the excited state. So you have to excite the atom in some way. You put the atom in a cavity made of two mirrors. The atoms are in the upper state. In fact, it's wrong. It should be in red, not in blue. The atoms are in the excited state. So what happens? There is, of course, some spontaneous emission noise. but this noise is amplified because the atoms are excited. Photons are bounced back and forth in the cavity, get amplified, and the amplification gives rise to radiation. One of the mirrors is semi-transparent, and some of the radiation gets out, and this is a laser beam, which gets out of the cavity. But again, this was long before Einstein discovered that, long before the experiment was possible. What I also want to stress is that what stimulated emission shows something which will become important in the second part of the lecture, the fact that the photons have a tendency to group in the same mode. If you have photons in a mode, they would like to get more photons in the same mode. So there's a kind of gregarious character, which is very important, and that I will discuss just after the break. What I want to adjust on this transparency, I summarize the difference between a source which emits spontaneously light and a laser source. Spontaneous emission, which is a kind of emission you get from the sun or from classical lamps, photons are emitted in all kinds of direction with all kinds of phases and frequencies. So it's kind of chaotic light, the kind of light you have in this room, for instance. At the opposite, laser light is light in which all the photons are in step. All the photons are in the same mode, vibrate with the same frequency, and ideally with the same phase. So it's really what we call tamed light, domesticated light, as opposed to the wide light of classical sources. But Einstein was the guy who discovered the basic effect, but I'm sure he had not imagined all what we can do with lasers now. And this will be an important part of the lectures I will give later on. I will describe to you all what we can do with this tamed light as opposed to what we can do with classical chaotic light. So I will stop at this point. We'll have a 10-minute break, and I will talk about the gregarious character of photons in the second part of the lecture.